Let's go to section 6, final section in this talk, evaluation of predictive density matrix. In the last talk, I said in statistics, we often evaluate proposed estimating methods. I repeat this again here. So we evaluate the base estimate by Vivek et al. In quantum state tomography. This is the purpose of this section. And please note that our argument here is formally very similar to H. Sun's work in the last talk. Before going with the proof, we see the similarity between quantum state tomography and prediction problem in the last talk. The left up panel shows the entire space of this white panel shows the entire space of density matrices. And we assume that the true quantum system on this green sphere, which denotes a quantum statistical model or parametric family of density matrices. So true state is specified by theta 0 or shortly rho 0 on the sphere, on the surface. While right down panel shows the entire space of predictive distributions. And here we assume the true distribution of the future outcome denoted by P0, which is specified by the true parameter theta 0, is on the surface, green surface, which denotes a statistical model. This is our main assumption. So we can easily see the formal similarity between two problems. Let us briefly review the setting. Experimental data denoted by W is generated by the true density matrix through a certain physical measurements. And true density matrix, of course, depends on the true parameter theta 0. And our task in quantum state tomography is to estimate a density matrix depending on the experimental data W, which is denoted by rho hat W. And roughly speaking, we consider an estimate of the density matrix close to the true one is better. Again, we have to the definition of the closeness between two density matrices. And here we adopt so-called quantum relative entropy, which is in a sense a quantum version of Kullback-Leibler divergence. Indeed, it has very similar properties as Kullback-Leibler divergence. For example, even if it involves the matrix logarithm here, but the quantum relative entropy is shown to be non-negative. So this quantity is shown to be non-negative, and it equals to 0 when and only when two density matrices coincide. We only see the relation between quantum relative entropy and Kullback-Leibler divergence when two density matrices are commutative. If two density matrices are commutative, we can diagonalize both density matrices with a common unitary matrix. So we obtain diagonal form of P01 to P0D and P hat 1 to P hat D for certain orthonormal basis. And then we obtain the matrix logarithm of rho 0 minus matrix logarithm of rho hat is also diagonal matrix. In this case, we can calculate the quantum relative entropy from rho 0, the true density matrix, to the estimated density matrix. By definition, it is given by this form, but in this case, we obtain the summation of each diagonal component, P0j times logarithm of P0j over P hat j. And it is formally a Kullback-Leibler divergence from the P0 to P hat. Now we introduce the risk function in order to evaluate estimating methods in quantum state tomography. Please recall that the risk function is a generalization of the average error in statistical inference. And here we define the risk function as the expectation of quantum relative entropy from the true density matrix to the estimated density matrix. We take the average with respect to the data generating model or probability distribution of the experimental data W. And here we drop symbol 0 in the theta 0, denoting the true parameter. And for every parameter theta fixed, the risk is determined. And we want to minimize this quantity for every theta. But basically, we do not minimize the risk function for every theta, not for every theta. Thus, we take the average of risk function using a certain prior distribution of the parameter. So we call this the average risk. The average risk depends only on the density estimate. And this average risk is scalar, so we can consider the minimization of this average risk. And for two kinds of estimates, we can compare them. For example, suppose that we have two estimating methods of density matrix. Then we can say rho hat is better than sigma hat if and only if the average risk of rho hat is smaller than the average risk of sigma hat, and so on. Okay, now finally we achieve the optimality result in quantum state tomography. According to Tanaka and Komaki, 2005, Bayesian predictive density matrix achieves the minimum of the average risk function. Here, Bayesian predictive density matrix is given by the following formula. But we can see that it is a simple average of density matrix using the posterior distribution of the parameter theta. Well, this is the optimality result. Now, let's summarize today's talk. For every quantum statistical model, every prior distribution, and every data generating model, Bayesian predictive density matrix is the best estimate of density matrix. And quantum relative entropy, it is an extension of Kullback-Leibler divergence as a measure of the closeness. But we note that this is not the literal prediction anymore, because it is a problem of matrix estimate, and it lacks the meaning of prediction anymore. Okay? But finding the formal analog to predictive distributions seems useful. Evaluation of statistical methods in some situations. This is a very important thing. Thank you for your attention, and this is the end of the talk part 2.